Okay, good morning, everyone. So it's 8 o'clock in the morning, and I just want to say good morning. And we're back. The PAASE webinars are back. So we'll be having our lectures again every Friday after the very successful 40th anniversary of PAASE. So today, our speaker will talk about finite element analysis on semiconductor packages. He is a full professor and research fellow at the Mechanical Engineering Department of De La Salle University, Manila, Philippines, and is the head of the Thermochemical Analysis Laboratory at De La Salle University, Laguna campus. His research includes finite element analysis, computational fluid dynamics, process integration and optimization, and energy systems modeling. He has published more than 100 Scopus Index journals in the national and international level. He has been selected as one of the 2017 Asian Scientist 100 for his contribution in the sustainability field. He is multi-awarded scientist in the Philippines, and among his national awards are Outstanding Scientist, Young Scientist in 2016, which was bestowed by the National Academy of Science and Technology. He is also a recipient of the Fulbright Scholarship Program at the University of Arizona and Texas A&M University in 2013. So let us all welcome Professor Aris Obando. Okay,
Thank you
Aris, you
very
may
much.
start.
Thank you, Kay. So the title of my presentation this morning is Finite Element Analysis on Semiconductor Packages. And to facilitate the presentation, I have here the outline. So we'll tackle first the overview of the semiconductor industry and focus on the contribution of the Philippine semiconductor and electronics industry. And we would go into some of the details of finite element analysis, at least just to understand how we would apply FEA in semiconductor industry. Then I'll be presenting a case study in the application of FEA in BGA packages, which we try to simulate and predict the crack propagation in this package. And I'll be presenting the next steps later on. So just an overview of the semiconductor industry. Semiconductors have been essential to various operations in different fields. It is fundamentally linked to how technology brings forth convenience to our society. From the early radio receivers to moon operations and now in autonomous vehicles, the semiconductor industry has helped in achieving these milestones, and its long-term growth prospects remain bright. However, present circumstances and COVID-19 pandemic provide challenges in the industry. Here we have a trend of the semiconductor industry, wherein we are seeing a decline of about 12% in the global sales compared to 2019. And prediction from the World Semiconductor Trade Statistics shows a slight increase to about 426 billion in 2020 after considering the negative impact of the pandemic on the global economy and supply chain. So an overview of the semiconductor industry. The factors responsible for the industry growth include the rising demand for consumer electronics, the growing automotive semiconductor market, the booming Internet of Things market, and lastly, heavy investments in new product development and research and development for these packages. So let's start first with the where it originated, which is in Silicon Valley in the States. It was in the early 1950s and 1960s when the semiconductor and electronics technologies were refined to be able to ease our daily living. It was right in the Silicon Valley, named after the most important element involved in microchips, where these room-sized machines turn into devices that fit into our pockets. And in this slide, we would see the Silicon Valley ecosystem, where Silicon Valley is home to a variety of business organizations and institutions that create an ecosystem for startup cultivation by providing an avenue for human resources and capital to interact and synergize to accelerate innovation processes. Focusing on high-tech edge, the Silicon Valley is also the birthplace of most disruptive business models and successful technopreneurs necessary for societal advancement. But if we look at the Philippine semiconductor and electronics industry, we can see here that it's divided into two clusters. Called the Semiconductor Manufacturing Services or SMS, which comprise of 27 which is 73%. So mainly here we can see that the it's more of the assembly and test of electronics component are the main drivers and businesses here in the Philippines. In this slide, we can see that majority of the country's total export come from the semiconductor and electronics industry. However, there is a decrease in the export from last year and compared to this year for the first quarter, and it's reflected in the total decrease in the export. So the country's performance in the SEI is affected by the COVID-19 pandemic and changes in the global market and supply chain. Most of the SEI are mainly found in Metro Manila, which is 52.11%, in Calabar Zone, around 40%, North and Central Luzon, around 5%, and lastly, we have Cebu of roughly 3%. So as of 2017, out of all these SEI, uh, there are less than 5 companies in the S&E industry which has a research and development department that focuses on R&D and design of packages. So mainly the business is really towards assembly and test or subcontracting the assembly of electronics and semiconductor packages. So challenges in the Philippine SEI, there is a lack of locally produced semiconductor products. Second, the current cost of product development is highly reliant on the conducting prototyping testing to check for functionality. In order to leverage the SNE industry and compete globally, there is a need for the following. We need a steady pool of skilled engineers who can actually do the specific details of packaging and development of packages and development of materials. Continuous professional development of engineers focus on specific areas of the SNE industry and aggressive leadership and direction to localize research and uh, requirement for us to be able to address these challenges in the Philippine semiconductor industry. So currently, we were able to secure a government funding, which is under the Philippine Department of Science and Technology, under the Collaborative Research and Development to Leverage Philippine Economy, or in short, the Cradle program, which aims to synergize the relationship between the academe and the industry to invigorate the Philippine R&D through collaboration of the two organizations, wherein the amount is granted to the higher education institution. So we were able to have or acquire a grant of amounting to total of 6.6 million pesos, wherein 5 million of that is coming from the DOST T-shirt Cradle project, and the industry collaborator contributed 1 million, um, 1 million pesos, and the counterparty contributed 0.6 million or 600,000 pesos. The Finite Analysis Laboratory, which is actually one of the output of the project, is currently situated at the Milagros del Rosario building at De La Salle University, Laguna campus. And this is a strategic position because a Philippine-owned semiconductor industry or company, which is only about 1 kilometer from together with me, I'm working with Engineer Jeremiah Gonzaga, and we have hired four RAs. We have Eman, Nino, Louis, and Patrick as the RAs. And we have partnered with Mr. Enriquez the industry. And we have Dr. Richard Di Magiba, who's a consultant to IMI and also a project manager. So the project framework, the finite element analysis would be part of the design and development of the company, wherein they would try to, instead of doing an experimental approach to test their designs, to test their ideas in the packages, they would try to apply a simulation-based, a computational simulation-based approach for them to see uh, the possible result or behavior of the package while they are introducing some of the factors in the package and in their processes. So we are currently helping them to enable the design and development by applying FEA with thermomechanical analysis approach for us to be able to see the behavior of the proposed ideas and projects in the company. Then the company would try to validate this experimentally in their line and will be able to compare our results with their results. So let's go now to the details of the finite element analysis. So finite element analysis, or FEA, it is a numerical method for solving problems of engineering and mathematical physics, useful for problems with complicated geometries, loadings, and material properties where analytical solutions cannot be obtained. FEA cuts or mesh a structure into several elements. So we try to subdivide this into smaller pieces in terms of its structure. Then this is reconnected to what we call the nodes, where actually the calculations happen. So some of the applications of FEA can be applied in the mechanical, aerospace, civil, and even in the automotive engineering field, it can actually be applied for structural or stress analysis, under which we can do a static or a dynamic analysis, a linear or a nonlinear solution. This can also be applied, concepts can be applied for fluid flow, heat transfer, electromagnetic fields, soil mechanics, even acoustics and biomechanics. So the fundamentals of FEA can be captured through, of course, different engineering phenomena can be expressed by a governing equation and boundary condition. So FEA approximate this into a set of simultaneous algebraic equations. So in this case, we have K times U equals F, where K, say we have a set of material properties. Then we have U, we can assign U as the behavior that we want to investigate, and F would just be the action applied in the simulation. And what we want to do is to isolate U, solve for U. And we have here different types of analysis for elastic, thermal, fluid, and electrostatic, wherein we have sets of K. We have stiffness for elastic analysis, conductivity for thermal, viscosity for fluid, and permittivity for electrostatic. And we would try to solve for the behavior U. So we have a set of behaviors for the different analysis. In our case, we have displacement, temperature, velocity, and electric potential, respectively, for the different analysis. And of course, the action, which is also given in this case. So we have either force, heat source, body force, or charge, specific for each of the analysis. So in this case, we try to solve for U, and U would just give us a trend and be able to use the information that we got from the behavior in and try to improve the process or the material properties involved in the study. So main principle of FEA, if we have an object on your left side here, we would try to subdivide this into smaller elements as shown here. Um, and these elements would give us somehow a better understanding of a specific area. And these are connected by the nodes, which are just the intersection as shown in this figure. This is quite important because the nodes is where the equations are being solved. So, of course, if we want an accurate solution, we would want to have more nodes, or we would have smaller elements, and that would actually give us a better accuracy of the solution. However, we also have to balance the uh, computational time, because the more nodes we have, that would actually entail more simulation time. So here, if we have a real world problem, we would try to simplify this into a physical model, perhaps using a CAD software, and also apply meshing. As you can see here, the simplified model has been subdivided already into smaller areas or volumes, wherein we can distinctly see the intersection, which are the nodes. So here, these are the main steps, initial steps in doing the FEA analysis. Once we already have the model, the next step there is to discretize the problem, of course, the equations, the partial differential equations that we are trying to solve. And This would enable the computer to be able to solve the specific problem. So we would apply an iterative solution to actually solve the behavior that we want to investigate or understand. Then once we already have done that one, we would need a software or a code for us to be able to solve for you or solve for the behavior that we want to understand. So usually, depending on the size of the problem or the solution, the time of computation actually depends. So sometimes we try to apply some simplifications in our solution, in our model, uh, for us to be able to balance the accuracy as well as the computational time for each of the solution. So advantages of FEA, it can handle very complex geometry and can be applied in a wide variety of engineering problems, can handle complex geometry, and overall, if you would see the process in semiconductor industry, can actually save time and money by eliminating the trial and error experimentation in the line. It creates more reliable and better quality designs. Uh, and also, it can give some visualization that actually the experimental approach lacks. However, there are some disadvantages because it's an approximation approach, so it only approximates the solution and it won't be able to get the absolute solution. Thus, it would lead to some errors. But of course, we have to manage the errors in the simulation. That's why we set some convergence threshold for us to have an allowable, acceptable error for our solution. And mistakes by users can be catastrophic for the solution, as we all say in modeling, garbage in, garbage out. If we actually input some erroneous data or some of the assumptions are not considered, then therefore the solution might be also erroneous. So just to show you some of the uh, sources of the inherent errors, if you have a specific domain here, if we try to apply the meshing approach, then we would have an approximated domain here wherein it's the whole domain is not really captured in this case. So what we try to do is just to simplify the model for us to be able to solve it iteratively using a computer. In terms of the field quantity assumptions, if we try to quantify a true deformation, we would result to some erroneous data. Say, for example, here, if we try to apply a linear element, and you would see here the differences. Also, if we apply a quadratic element, there is some differences in the the data. So here, these are some of the sources of the errors in the use of FEA. So we just try to manage to minimize the error and try to uh, be able to identify initially an acceptable tolerance for these errors, wherein we would be able to say that at least the results are quite close and indicative of the possible behavior of the solution. So just to give you an idea of the general procedure of FEA, we have classified this into three processes. So first, we have the pre-processing, which includes the selection of the analysis, the meshing, the selection of the type of element. It can be 2D, 3D, linear, quadratic. the assignment of the material properties, and the application of the boundary conditions and load. Then we have the solution, wherein we select the appropriate solve the boundary value problem. Then once we have already the results coming from the solution process, we now apply the post-processing wherein we display the results. And we try to analyze and perhaps show a better figure for the behaviors and the results of the modeling process. So allow me to present a case study. This is already a published work in Engineering Failure Analysis Journal. So the case study is, the paper is entitled Finite Element Analysis on the Factors Affecting Die Crack Propagation in VGA packages under thermomechanical loading. So this is a MS work by one of our graduate student, Mr. Nino Rigo Emil Lim. Just to show you the progress in the semiconductor packages, it all started in 1970s, and as you can see, the packages have bigger and bigger sizes and have some copper leads and legs as shown in this figure. But in the advancement of the packages, uh, the development has focused on a higher density in a smaller package, wherein the VGA packages actually emerged very recently. So what is a ball grid array? The ball grid array has become increasingly popular for surface mount packages or package ICs that require high density connections with less surface area. Using the underside of the IC package rather than connections around the edge, this enables connection density of the reduced and simplified PCB layout. It uses solder balls to electrically connect the silicon inside the VGA to the surface mount package ICs. So as you can see here, we can see that the VGA package are quite small. However, it has a high density capacity inside this very small package. We applied a thermomechanical analysis, which is a technique used to measure dimensional changes of a material as a function of temperature and force. Thermal and mechanical loads are involved in this type of analysis where the response or behavior of the model is observed. Another aspect that we have considered in this study is to track the crack propagation analysis. And for us to be able to quantify uh, the crack propagation, we have used the J integral. And the J integral represents the way of the calculation of the strain energy release rate per unit fracture surface of the material. So this method is used in calculating the energy release rate of a material. Since in the package, the heart of the package is the silicon, so here we try to be able to get from the available literature the critical energy release rate for silicon, which is 0.002 millijoules per millimeter squared. So this is coming from the work of Ibrahimi and Kalwani in 1999. And in this analysis, we were able to use a commercial package, which is the ANSYS Mechanical, with which actually can do finite element analysis applied on structural components. various components of the BGA. As shown here, we have the epoxy molding compound, which is the EMC, which is the mold compound here. The silicon dye, as shown in the yellow figure, of course, and the solder balls are shown in the figure. So we have considered the modulus of elasticity of different components. We have alpha here, uh, of course, the glass transition temperature, and of course the Poisson's ratio. So here we have considered the dimensions of the BGA to have a 34 mm by 40 mm. But for the simulation that we've done, we try to apply constraint wherein we just model the quarter part of the BGA package, since we found that the BGA package is somehow symmetrical to this section, a quarter portion of the package. So just to highlight this modeled area, this is basically the area that we have simulated for the study. So you can see here the die, the mold substrate on the top view. We have applied a methodology wherein we try to develop the model, develop the geometry, also to gather information on the material properties. Then we conducted a thermomechanical simulation by initially doing a mesh independence test. So we try to ensure that the meshing is appropriate for the simulation and have done some initial testing of the mesh. Then we try to do a model validation and existing experimental study and a computational study. We try to replicate that just to gain confidence on the simulation. Then after the validation study, we try to do the crack propagation analysis. Here we have applied in the meshing strategy conformal meshing. We also utilize localized meshing for specific for the area of the crack, and have also done its own mesh independence test specifically for that area. Then we have applied a two-prong approach wherein initially we try to screen first the factors affecting the crack propagation by applying definitive screening design approach. Once we have identified the most significant factors, we then applied a RSM or response surface method through a central composite design uh, to see a more comprehensive behavior of the crack propagation with considering the most significant factors. Then we try to do a prediction model out of the RSM results. So under boundary condition, we have here the application of the symmetry on the left side and the right side of the quarter model. Then we try to apply a point and edge constraint in this section. As you can see at this intersection, the center of the package, we try to apply a point constraint at the top corner wherein we set dz to be equal to 0. So just to fix any movement at this point, and also this apply dx and dy to be equal to 0, just to fix this area, the center of the package in doing the simulation. Then we have applied a ramp up of temperature and the thermal load for the simulation from room temp. And mainly this is the process being simulated from room temperature. We heat it up to 210 degrees Celsius and try to understand the crack propagation behavior of the BGA package. And also to for us to be able to quantify uh, the warpage measurements at this point. If we are looking at the package here at letter B, we try to apply, of course, initially for the whole package at point B here, we try to do some introduction of the crack location or the initial crack propagation. We have in this section the corner of the die as shown in this figure. So let's look at the validation results. We try to compare this with the study of Tsai et al., who actually looked onto the plastic BGA back in um, back in an experimental study, which is shown in the red line, and a two-dimensional FEA shown in the gray line. So based on the FEA results, we have developed a 3D model and compared the experimental and the two-dimensional FEA model of Tsai et al. And the validation results have shown a good trend compared to the two initial results. Then we proceeded with the screening design. So this is the factor screening. What we try to do here is to consider first 8 factors. We have die thickness, the substrate CTE, which considers the movement X and Y axis, substrate CTE Z. We have the epoxy molding compound CTE, and also the glass transition of the EMC or the epoxy molding compound, as well as the modulus of elasticity of the EMC and the residual stress. And lastly, we have the crack length. And we have performed 17 runs for the combinations of the factors, the 8 factors for the DSD. So the results of the DSD, it showed here that we have 4 highlighted factors. So we have a p-value of less than 0.05, which indicates that these 4 factors are the most significant factors in terms of the crack propagation. So we have die thickness, we have the epoxy molding compound, glass transition temperature, substrate CTE, XY, and the initial introduced crack length are the 4 significant factors for the crack propagation. So now that we have identified the 4 factors, we try to apply a response surface method focused on the 4 factors identified. And this resulted to 26 runs with the combinations of the values for the 4 factors. As shown here, the green line actually quantifies the critical energy release rate for the silicon, so that we know if any of the lines touches the green line, we know that there is a high the silicon die or would actually crack, propagate the crack that we actually initially introduced. And we have here the interaction results, and you can see here that the combination of glass and the substrate CTE for X and Y, there is a huge probability that the 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 crack propagation would actually propagate. Then we also applied a prediction model for this, wherein we have considered the worst case scenario, which is shown in letter A, What if we try to quantify the factors for the values for the four factors, and and see how it would actually go. So we have quantified that. At the same time, we have identified the scenario wherein we can identify the critical crack length, which limits us to the energy release rate of the silicon, which is uh, uh, 0.02 millijoules per millimeter squared, which is the result of letter B. And this can be actually used in the visual inspection for the initial crack coming from the different processes. This shows you the contour plot for the results. And the results this would be approaching the critical energy release rate for the silicon. So we might want, in the engineering standpoint or in the R&D standpoint, we may want to focus on the blue area or the blue line, uh, for us to be safe that the crack won't propagate with these types of condition. So the contour plots can be used in the line by implementing, of course, different material combination of materials and working together with the supplier to attain such material properties in order for the uh, to lessen the probability of the crack propagation. So in conclusion, we are able to develop a 3D, 3-dimensional FEA model of the BGA package, which we actually compare with a initially conducted study, an experimental one, and a two-dimensional model. And we have compared the warpage measurements, and they actually have a good agreement with the study of Tsai et al. And we have applied definitive screening design approach, which identified the four significant factors that affect the crack propagation in the silicon die. And we found that die thickness, glass transition temperature, the substrate in plane CPE, and the crack lengths are the four factors that significantly affect the crack propagation. Then we applied a response surface method. In here, we were able to produce the interaction and contour plots for the energy release rate or the crack propagation in the design of the package, as well as the working with the supplier to attain those material properties for us to somehow minimize the possible crack propagation in the silicon die. So results, a thinner die with a relatively higher substrate in plane CPE will most likely result to die crack propagation. Lastly, we have using the developed predictive model, the detection criteria for wafer saw cracks can be established. So we hypothesize that of course, before doing the assembly, the silicons coming from the wafer, it's actually being sawn. During that process, there are some initial cracks, very minute cracks that can possibly propagate in the assembly line. So yeah, so that is the results of the study. Next steps, we are currently working with the industry under the DOST Cradle together with IMI, and we're looking into continuing the project, and hopefully we can secure the second phase for the DOST Cradle for us to focus on packages applied on autonomous vehicles. So that's what we would be focusing on phase 2 DOST Cradle. So again, that actually ends my presentation. So thank you very much. I can now answer some questions.
Okay, thank you very much for that, Aris. It was a really interesting presentation. So I'd like to remind our audience that if you have any questions for our speaker, you can either choose to raise your hand and I can call you out. I can call you out so that you can ask the question directly, or you may type on the chat box, which you can find at the bottom of your screen on Zoom. Okay. So yeah, so maybe I can start off the questions. So I really think that this is a very interesting work, and it's good that you were able to collaborate with the industry. So I'm just curious. So based on the initial results that you've had, or the initial studies that you've conducted together with IMI, um, what's the feedback from the industry? Like, how did they find this particular approach for their products?
Good question. They have reiterated that this process, we're actually doing a weekly meetings with the IMI engineers together with the managers. And currently we have two simulation. We are serving two teams under IMI. We're doing some simulations with them, applying the models that FEA model that we have discussed this morning. And they actually need help in doing these types of simulation since, of course, they are only limited with the experimental. They also mentioned that they have acquired similar softwares and computers. However, uh, their direction is really on manufacturing. So they have
Mhm.
limited capability in doing the simulation. However, the management already acknowledges the need for this type of study, this type of approach for them to actually save money and time in validating. Of course, being able to see the behavior of the package is quite uh, really difficult since the current method they have is destructive.
Mhm.
So if
Yeah.
there's already a complaint of the customer, that's one of the feedbacks. If they are able to capture or catch that in the line before even going to the customer, then that would be good. They can do some initial initial improvement, process improvement, material revisions. However, ideally, during the design phase, we Intel actually applies a 2 to 3 or even 5 year planning. They try to design different configurations for the packages
Mhm.
before they even roll it out to production. Um, they would want to apply this method and try to validate later on in the line if this actually is replicates the physical behavior of the package. Um, and just to take note, of course, I already mentioned most of the businesses, semiconductor businesses here in the Philippines, focus on assembly and
Yeah.
test. And assembly and test really, if you're a subcontractor, you would be given already the design and the specifications. You just need to manufacture the material. So the design phase is not really part of the uh, huge business here in the Philippines. However, there are some huge companies, huge players in the industry that have their design here. Lucky for them, they can actually validate it using this approach before they even roll it out for manufacturing.
Okay, thank you, Aris. I think Joel has a question. Joel?
Thank you, Kathleen, and thank you, Aris.
Thank you,
Aris, your
Joel.
presentation was very methodical and very informative, so thank you. I just want to get a little bit more information about IMI, the Integrated Microelectronics. Did you say that that is a Filipino company? Yes,
Yeah,
okay.
it's a Filipino-owned company. It's under Ayala, uh,
Right.
and they're also listed as one of the PSE companies, Philippine Stock Exchange
All right.
companies.
And are they doing only manufacturing and testing, or do they have their own original design?
Based on their management, that's really their bread and butter, the assembly and test. They actually manufacture. However, the manager that we are collaborating with has expressed that they are already starting their own line of products because
All
they
right.
already have those capabilities. So it's high time for them to actually come up with their own products, develop their own products.
That makes absolute sense. And for the packaging that you worked on and that you modeled, did they design that packaging, or was that a specification that was provided to them?
The package that we have simulated is a different package from what they are actually doing, since they're mainly focusing on a specific package for the automotive industry. However, just to be able to show the method on how it is done, so we have selected the VGA package, and it's a quite common package nowadays in our cell phones, in any electronic devices. It actually uses a VGA package.
And last question from me. So with the results that you came up with, and I'm sure those are recommendations you provided to them, are they then making adjustments in their manufacturing of the packaging so that your recommendations are actually implemented?
Uh, yes, indeed. Since our meeting is on a weekly basis, so the results of the simulation, or even before we start the simulation, we are working together with the engineers to be able to capture the appropriate material properties, the boundary conditions before. So that their team and our team has to agree that this is the correct model that we are solving. And once we have already the results, we present it together with the managers. And since the managers are there, they can implement some corrective actions. If the corrective action would need, they would need to coordinate with their supplier just to tweak some of the material properties or explore possible change of the material for them to be able to get the results that they need in the line. Then they would do that action, and we have seen that in our previous meetings. However, if the result would recommend that there needs to be a process improvement, then of course their engineers are there to capture the recommendation. Again, in this result that I presented, one of the recommendation is to tighten the visual inspection for the material.
Mm. All right. Thank you, Aries. Thank you.
Okay, thank you for that, Joel. Yeah, let me wait for Aris. He's frozen on my side. Aris, are you still there? I have a question for Aris.
Usually,
Aris, can you hear us?
yeah, I
Okay,
think
okay,
I
okay. Yeah, the internet might not be as stable. Okay, we have a question from one of our viewers here with us at Zoom. It's Juanito Decina. He was asking why was the die attached material not included in the model?
the die attached not include. The die attached. We actually initially included that. However, we found in our initial results that it's not really significant since the die attached material is quite thin. So it really didn't affect the warpage. It's not a major concern in the simulation. So in the simplified model, we have excluded the DA material.
Okay, based on just a follow up question for me. Based on the model that you selected, so how close was it to the real performance of the packages?
Yeah, I think that's a good question. And one of the uh, one of the questions here is how do we now validate the
Mm-hmm,
results?
mm-hmm.
Uh, so what we do in our project is to really weekly present the results with
Okay.
our partner. Um, so once we have presented the results, their engineers would also present their result. Say for example for Warpage, they would present it and see how far we are in the simulation. And we have also defined some of the criteria, like we have defined the percent differences of acceptability. If we define, say for example, for this component, acceptable difference would be 10% difference. In our case, we were able to attain less than 5% difference. So we would accept that result. Else, we would go back to the drawing board and
Mm.
see where we can improve the model to be able to get the desired results or behavior.
Okay, we have another question. This comes from Leslie Diaz. So, why is crack propagation the focus of the simulation? What about crack initiation? So, silicon being brittle by nature, it will propagate cracks so easily, but initiation would be difficult to initiate.
Yeah, I think that is a good question. Uh, the question there was really if we want to already quantify the crack or be able to capture the crack, um, then it's gonna be a process related solution on the saw process.
Mm-hmm.
However, in this case, uh, the wafers are already received by the company, or the cut uh, silicon dies already received by
I
the
see.
company. So therefore, perhaps in the wafer uh, development facility, they already have cut the wafers. So there's already the minute crack. So again, for the company, they just need to check the minute cracks initiated already in the silicon and communicate that with the uh, wafer development company.
Okay. Okay, there's another question from Juanito. Were there also simulations done considering differential expansions along the x and y directions, but were also excluded in the final study?
I've shown a while ago the fixed point and the fixed edge for us to be able to know what are the fixed constraints in the simulation. So we actually allowed the model to expand on different directions, but already constrained on the center of the model. So we didn't include the animation, but if you would see the results of the war page as well as the crack propagation is actually X and Y, and we can also see some results in the Z direction.
Okay, thank you for that. So, are there any more questions from the audience? Okay, so maybe Aris, are there any final words that you'd like to impart to our listeners? Maybe either for those into semiconductors or those who want to explore doing research on finite element analysis.
Yes. So thank you, Kay. So currently the team is still under the DOST Cradle project, and we're actually tasked to coordinate with SAFE for us to be able to showcase the method that we are able to do and offer it to the other companies. And we're very open for collaboration. And also, I took this opportunity to present in PAASE, since I know for a fact that most of our engineers and scientists are in the US, are involved on semiconductor packages, also designing similar inventions. So we're hoping that to collaborate with them later on, apply the same models, and we can also perhaps explore some of the multi-scale models that we can apply for this type of problems. And all of those are in the efforts to improve the semiconductor industry here in the
Mm-hmm.
Philippines.
Okay, thank you, Aris. Joel, do you have anything to say? Yeah.
No, I just wanted to
Okay,
say
all
thank
right.
you and
Uh,
congrats.
Okay, but
Thank you.
before
Thank
we
you so much,
close, okay,
Alan.
thank you very much, Aris, for that presentation. But before we close, I just wanted to invite everyone to our next webinar. So we'll be doing this regularly again every week on Fridays. So I'm calling all other PAASE members who haven't done their webinars yet that you might want to do your webinar soon. Okay, so next week we'll be having Dr. Elmer Mojica. He'll talk about probing dancing molecules with Raman spectroscopy. So for those of you who would want to join us next week, so we'll still be on the same time. That's from 8 to 9 in the morning for the Philippines on Fridays, but it will be on Thursday nights for those of you in the US. So please register at bit.ly/emojica. And
All
then,
right.
yeah, so I'd just like to remind everyone that you can find Paase on Facebook. We also have our own page, which is at paase.org. And we just recently concluded our 40th anniversary celebration. So the links to the recorded lectures can be found also in the website. And for our Paase webinars, which we do every Friday, so we upload the recordings of the webinars in our YouTube channel, Paase Webinars. Aris, maybe can I also request to get a copy of your presentation if you don't mind, so I can share it also with our
Yes,
registrants.
right.
Okay,
Sure.
so
I'll send it
All right.
through you.
that's it, everyone. Thank you very much.
Thank you very
So
much. So
Bye all.
Dr. Elmer
Bye.
is
Thank
here
you,
with us. So
Hardy.
Dr.
Thank
Elmer,
you.
I'll see you next week.
Hey,
Looking forward to your talk. Thank you, guys. Have a good day ahead.
Thank
thank
you.
you.
thank you.
Bye.
Thank you. Thank you to Karis, Abiso. Thank you for the invitation.
Yeah.
Thank you.